We have spent the last two lectures talking about the on-chain part of Plutus, the validation logic that is compiled to Plutus script and actually lives on the blockchain and then is executed by nodes that validate the transaction. And there's a lot more to say about that on-chain part. We haven't looked at more complex examples of validation yet that make more sophisticated use of the context and actually look at the inputs and outputs of the transaction. And we haven't seen how native tokens work yet. So Plutus script is also used to validate the minting and burning of native tokens. And we'll definitely have to talk about those topics and come back to that. However, before we go into too many sophisticated topics of on-chain validation, I don't want to neglect the off-chain part because that's equally important. The on-chain part takes care of validation, but in order for there to be something to be validated, we must build these transactions and submit them to the blockchain. And that's what the off-chain part does. So I want to start talking about how to write off-chain Plutus code in this lecture. And unfortunately, there's a slight problem concerning the Haskell features needed. So the on-chain part that we have seen so far is somewhat alien and needs some time to get used to due to the fact that we have this compilation to Plutus script. But we don't really have to worry about that if we accept that there is this template Haskell magic. The validation function is just a plain Haskell function. And it's actually a very simple Haskell function from the technical point of view. We don't use any fancy Haskell features to write this function. And one of the reasons for that is the way Plutus compilation works. I explained that in principle, in these template Haskell quotes, we need to have everything, all the code inside these quotes. And we can get around that using this inline pragma, but that still means that everything we want to use, all the helper functions, combinators we want to use, must have this inline pragma. And because the standard Haskell libraries don't have it, we have the Plutus prelude, for example, that is like a copy or it's similar to the Haskell standard prelude, but it adds these inline pragmas to all the functions in there so that we can use them in validation code that gets compiled to Plutus script. But of course, there are hundreds of thousands of Haskell libraries out there, and most of them weren't written with Plutus in mind, so we can't use them inside validation. And that has the effect that the Haskell code inside validation will be relatively simple and not have many dependencies. So it's really just a plain old Haskell function. It gets these three arguments, the datum, the redeemer, and the context, and returns a Boolean. Or maybe a fourth argument if you parameterize your contract. And somehow in the off-chain part of Plutus, the situation is reversed. We don't have to worry about compilation. Nothing gets compiled to Plutus script. It's just Haskell. So we just write plain old Haskell in the off-chain part. But the flip side is that the way this is implemented, the way that works, uses much more sophisticated Haskell features, quite advanced Haskell features, so-called effect systems and streaming, and in particular monads. So all the wallet code, the off-chain code, is written in a special monad called the contract monad. And monads are very infamous in the Haskell world. They are normally the first stumbling block for beginners, for people that are new to Haskell. And there are a lot of tutorials out there that try to explain monads. Monads get compared to burritos and all sorts of metaphors to try to explain the concept. But I thought I should at least try to give a crash course in monad for those of you that are new to Haskell. And I do realize that that will be a bit boring for people that are already familiar with Haskell. But you can just skip ahead until I get to the actual contract monad that is relevant for the wallet. So I want to start with the a brief, quick introduction to monads.